Okay, that's why there's a for loop there. That for loop is going to do this part first, and then do the second part, do the third part. While we are doing all this, what we need to do is we have to compute the sum, right? So this sum is shared. But the problem is if you have 16 threads trying to write into this sum, we're going to re-modify that. Okay? And therefore it will have race condition. Okay? Race condition because every thread trying to re-modify this shared memory. Okay? And therefore they have race condition. Now to overcome that, that's why we have this 2a. Okay? This 2a, what we do is first we want this sum to be shared still. Okay, so it's shared still, but we make it as partial sum, and we separate all this partial sum. Okay, separate it so that we have individual element of this partial sum, and it's going to be handled by individual threads. So each individual thread is going to sum here, and because it is using their own individual element, they're not going to have race condition because they're not going to override one another, right? Okay, so each thread is going to sum partial sum, and all of them without any race condition. Fine. Now we have one more problem. Eventually, all these partial sum need to be summed together into this shared sum. Into here. But if all of them try to do on their own, okay, they're going to sum it, they're going to face race condition as well, isn't it? They're not? Because, of course, they do partial sum, no race condition. But once they are all done, we're going to sum it. And everybody is going to write into here, and we will still have race condition. Okay? So that's the reason why we use thread 0. And we have a for loop outside this OMP parallel. And this thread 0 is going to go into the for loop, take each one of them, add them up together into this sum. Okay, because it's only thread 0 doing it, so there is no race condition because one person doing it. One person do for all. Okay, the rest do the computation, and we choose thread 0 to sum them up. So basically, we don't have race condition in part A. Okay, we overcome it by first making sum into partial sum and asking thread 0 to sum them up together. So we don't have race condition at all. Okay, but we have fault sharing. Because our partial sum, the data is next to one another. Okay, so when the CPU read the cache, you read one cache line, and this cache line goes into the cache in the CPU, and the thread try to access each individual element because they are inside the same cache line. They have to wait for one another, so it slows down the system. So what we do part B. What we do is we put them far apart by padding. Okay, we create two-dimensional array and we pad it. Okay, so by doing that right now, if let's say the CPU read this cache as a cache line, it read this as a second cache line. So right now this data is in the different cache line, and therefore the CPU is not the thread will not share this cache line, and therefore it will not wait for one another, and it will run faster. And we can see the result, right? This one is slow, this one is fast. When we do we do this padding. Okay, so this is about 4 times faster than this, right? Because we don't have fault sharing. Okay, now the code that is given here, P4, PQ1, is actually the code for this. It's a working code for this. Okay, it's all written here. You don't have to do anything.